Hello and welcome to another video. In this video we're going to be working on a linked list cycle. In this problem you're given the head of a linked list and you want to determine if the linked list has a cycle, and then you want to say true if it does and false if it doesn't. And so you're given the head of a list, and then you're given this position thing, and this is kind of telling you where the tail connects to the node, but you don't really have to worry about it. You can essentially traverse it like a linked list, and then there would be some under the hood stuff to do that part. So essentially you can treat it like a normal linked list, and basically you need to see if there's a cycle. So in the first example, clearly you can see a cycle, and a cycle just means there's like a circular path. So here there's one, here there's one, and here there's not. So how would we do this, right? Like let's say we have 3, 2, 0, 4. How would we determine if there's a cycle? There's a few ways, and some are better than others. So obviously one thing you could do is you could just go through the list and you can maybe like store each node in a hash map, and then if you visit it again, you would say if there's a cycle, right? So you'd go through the list, you'd start here, and you would store, because all these nodes are stored in memory, they'd be stored in different memory. So even if you have repeating values, like if you store this node 3 and then there's another node 3, they would be stored at a different memory address, so they wouldn't be equal. So how do we, how would we do this, and how would we do a better thing, right? So, but yeah, it's pretty straightforward. Essentially, you just have a hash map, and you just store the node. So you're like, at this node, you store node 3. You're at this node, you store node 2 in your hash map. Technically, I guess you could store like a hash set, probably. But either way, you would store 0. You would store 4. Then you would go back to 2, and you'd say like, oh, 2 is in my hash set, so therefore I need to return it. But we're not really going to talk about this solution because this one is not as good. Now let's talk about something else. So it tells you that there are 10 to the 4 nodes maximum. So another solution, you could say like, okay, well, if there's only 10 to the 4 nodes maximum, why don't I just traverse 10 to the 4 times, or 10 to the whatever, 10 to the 4 plus 1 times, and if there is a cycle, then I'm just going to repeat, like, right? So let's say I traverse this 10 to the 4 times. I would just be going in a circle, and a circle, and a circle, and a circle. And if there wasn't a cycle, I'd be out of bounds. So that's another way you could do. You could just say traverse 10 to the, whatever maximum thing you could do, 10 to the 4 plus 1, let's say. And then if you get out of bounds ever, then there is no cycle, right? Because you got to the end. So you're literally just saying, like, it would be an example of, let's say this is a road, and the longest the road could be is like 10 miles, right? And there might be a loop in the road, so you could just say like, okay, well, I'm just going to go 10 miles, and I either, go in this loop a bunch, or I get out of bounds eventually, because the longest the road can be is 10 miles. So that could work, but that's not the best solution, but that could work, right? So essentially, if you had no cycle, you would just have a 10-mile road or a 10 to the 4th number of nodes, and you just get out of bounds. That could work, but the problem is, for something like this, it would take 10 to the 4th operations, right? Which isn't great. So yes, technically, that's the maximum it can take, but it's always going to take that. And this should only take like 4 or 5. So is there a better way? And it turns out there is a better way. And the way to, there is actually a cycle detection algorithm. And obviously, if you haven't really heard of it, it's kind of hard to come up with on your own. But essentially what you have is you have a slow pointer and you have a fast pointer. And pretty much all you do is, so let me draw these out in different colors. So let's say this is our slow pointer, this is our fast pointer. Let's actually draw them out in different colors, and let's actually draw them over here so I can erase them later. So slow, start at the same place, fast. They start at 0, and you just have them go, and then either one of them goes out of bounds, the fast pointer, right? So the fast pointer is going to move 2 nodes at a time, and the slow pointer is going to move 1 node at a time. Right, so the fast pointer will go like 1, 2, 1, 2, and so on, and the slow pointer will move 1. And pretty much you just say, let them keep moving, and then if they ever intersect again, then there's a cycle. And if you think about it, if you have a straight road, and you have like 2 cars, let's say, and one's going 60 miles an hour and one's going 30 miles an hour, obviously they will never intersect again if it's a straight road that just leads to the end. But if it's a loop, then they're both going to be in the loop, and then they're going to intersect eventually, right? Because one car is going faster than the other one. So that's kind of like a good way to think about it, right? Like if you have a road, and this road is 10 miles, and this car is, one's going 60, and one's going 30, then they will never really intersect after the starting point. The 60-mile-an-hour car will just go faster and we'll get to the end. But if it was 5 miles, and then it was just like a 5-mile loop, right? So 5 miles of road and then a 5-mile loop that just kept going and going and going, then yes, the faster car would get there faster, but eventually they'd both be in the circle, and then the faster car would keep running into the slower car, right? It's like if you're on a track and one person's faster than the other, you're just going to keep lapping him and lapping him and lapping him, right? So that's kind of the same thing here. So if we take a look, they start here, and let's just kind of walk through this. So in the first iteration, the fast pointer will move 2, right? So it'll go here and then here. So it'll be over here. And the slow pointer will move over here, right? It only moves 1. And let's actually delete this now. Okay. And so in the second iteration, the fast pointer will move 2 again, so it'll go 1 and then a loop around here. So the fast pointer will be over here. And then we can delete this. And the slow pointer will move over here, right? It'll only move 1 iteration. So slow pointer will move over here. And then 1 more. So the fast pointer will move over here. So I'm just going to draw in the same color just for the sake of time, but fast pointer will move 2 and the slow pointer will move 1, and now they have crossed, right? So that means there is a cycle. And no matter what, they're always going to cross. Like, you can try this for all kinds of things, but essentially they're always going to cross. And if it was just a linear road with no cycle, right? If there was nothing here, then the fast pointer would just always be ahead of the slow pointer, and then it would just get out of bounds. So that's kind of what you do, is you just keep moving them forward, and then if the fast pointer ever goes out of bounds, then you have no cycle, because obviously you can never be out of bounds in a cycle, it's just a circle. And if it doesn't get out of bounds and they hit each other, then there is a cycle. So that's essentially what we're going to be doing. So that's all we need, and now we can code it up. So essentially we're going to make a slow and a fast pointer. They're both going to start at the head. And there is, it looks like there is also a thing for no nodes to be in the list, but we're going to account for this, so that's fine. So we're going to say, let's just, and here's a linked list, and here's what it looks like, right? So it has a value and has a next, but essentially we're going to say slow equals head. So we can actually set slow fast. We're going to make them both equal to head up the list. And then we're going to say while fast and fast.next, right? Because the fast node will move up 2 nodes. So in order for it to move up 2 nodes, let's say it's here, in order for it to move up 2 nodes, the node after it has to exist, right? If this doesn't exist, then it can't move up 2 nodes, and then you'll be out of bounds, right? You can't say like fast.next.next because there is no fast.next. So fast has to exist and fast.next has to exist in order for it to move up. So we're going to say fast and fast.next. Then we're going to say fast equals fast.next.next. And slow is only going to move up 1. And we never have to check if slow.next exists because fast should be way ahead of the slow. So if fast exists, slow will always exist. Then we just check if fast equals slow. If these are equal, then we can return true. Otherwise, if we ever break out of this loop, that means the fast ran out of bounds, then we can return false. And that's pretty much it. So we just have a fast and a slow, and the fast moves up 2, and the slow moves up 1. And if they're ever equal, then you have a loop. So let's try that. And it looks like it worked. And you can see it's pretty efficient. As far as the space, yeah, I mean, maybe you could do this with like using not 2 nodes somehow. Yeah, you definitely could do in 1 node with the thing that I suggested, right? Where you just have 1 node and it just keeps going like 10 to the 5th times. We can try that solution actually. But like I said, it's going to be slower on average. So we can literally say like, okay, let's just say fast, slow, or whatever, just like cur equals head. And then we could say like for I in range, say 10 to the 5th or 10 to the 4th plus 2 or something, right? We just want to make sure we do it enough times. And then we just say like if not cur, return false, otherwise cur equals cur.next. And then finally we can return true here as well. So I think this should theoretically work. Yeah. But you notice it's going to be a lot slower, right? So this is more space efficient because we're only using 1 node, but this is a lot slower. So we're going to go back to the other one. But that's just another way you could do it, to only use one node. And there we go. Okay. So this is going to be our solution, and let's think about the time and space for this one. So for the time, we are essentially going through this list, and we can go through it multiple times, but we're not going to go through it like too many times. This is still O of n, because yeah, you could go through this loop a few times, but it's still going to be like a, you know, roughly O of n. You're not going to go through like some quadratic number of times or anything. Okay, you might have to go through this loop, yeah, like a few times, and you can try like bigger loops and smaller loops, you know, but pretty much O of n time. And for the space, all we did was use a fast and a slow pointer, which are just two variables. They're not like arrays or anything, and we're only going to use two regardless of the size of the list. So if the list is like 10 to the 4th nodes, we're still only going to have a fast and slow. So it's going to be O of 1 times O of n. And yeah, it's going to be it for this problem. Pretty easy one. But if you didn't know the Floyd Sturgis and the Hare cycle detection thing, it's definitely not something you can come up with on your own, I would say. But it's definitely good to know for other problems. And you can also use this to figure out the entry point of a cycle and so on. So if you want to look into that, you can look into that. Like you can actually calculate where this cycle entry point is, which I did do in some other problems. And you can also look into that. Okay, but that's going to be it for this. And hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.